Hi, I'm Yoon. I'll present our work, Learning-Based Initialization of Trajectory Optimization for past following problems of redundant manipulators. The problem statement of the past following problem is as follows. We need to generate a joint trajectory precisely following a given 6-dimensional Cartesian path with an empty vector. The inverse kinematics problem is to find a joint configuration corresponding to a single pose. In this regard, we could consider the past following problem as an extension of the inverse kinematics problem. However, when dealing with a long sequence of poses, the joint trajectory should satisfy multiple objectives and constraints, many of which are highly non-convex in the configuration space. We also specifically address the redundant manipulator, which have an infinite number of configurations to represent a single end effector pose. This characteristic known as redundancy provides greater flexibility in motion, while requiring additional time and effort to plan a trajectory. In solving the past following problem, one approach is a sampling-based approach. Such methods create a discrete configuration graph composed of inverse kinematic solutions, and subsequently search for feasible joint trajectories on the graph. Although it's asymptotically optimal, these methods suffer from a high computational burden. Conversely, optimization-based approaches aim to reduce the search complexity. However, a notable drawback is the sensitivity to the initial guess. One potential solution is to employ sampling-based method. However, given a practical time constraint, this approach is still susceptible to poor local minima. This figure shows how the initial trajectories affect the optimization performance. With our proposed reinforcement learning-based initialization method, the optimizer successfully converges to the solution, while baseline approaches get stuck in local minima. The linear method linearly interpolates in configuration space. The greedy method selects the best inverse kinematic solutions within a limited time budget. Thus, the goal of this work is to generate an initial trajectory having a minimal objective function value as quickly as possible, to help the optimizer converge to a better optimal solution quickly. As a solution, we adopted an example-guided reinforcement learning to amortize the extensive online computation. Our learning framework was designed to learn an unified policy over diverse path-following problem configurations. This figure shows how we configure the training set. To collect the dataset, we employed an optimization-based motion planner. While the resulting data is suboptimal, it contains kinematically feasible null space motion information, since it's optimized on the sign distance field. To leverage suboptimal data, we proposed to project the imitation reward into the null space. The green line represents the performance when we naively mimicking the suboptimal data. In this bin, the orange line shows the performance degradation when the task reward is combined with the simple L2 imitation reward. However, our null space projected imitation reward boosts the training performance by resolving the confliction between the task and imitation reward. Thus, given a past following problem, our policy creates an initial trajectory in the configuration space by receiving the task space information. These figures show initial trajectories generated by our method. It shows the applicability of our diverse path-following problem setups. These problems were not seen during training phase. In addition, you can see in the yellow circles, the elbow tries to avoid potential collisions by leveraging the redundancy in the motion. To evaluate our initialization method, we prepared 6,000 benchmark problems. We also prepared first and second order optimization methods to verify across the type of the optimizers. The left figure shows the convergence performance of pose errors over optimization time. Our method, shown as the red lines, demonstrates superior convergence performance over all benchmark sets. We also measured the success rate. Notably, in the random cases, our method showed significant performance improvement compared to the representative initialization method. We also conducted experiments on a real robot. Our initialization method significantly reduces the total execution time. Our approach also provides a smoother trajectory, resulting in lower jerkiness for the controller to smoothly track. Thanks for your attention. For more in-depth analysis, please scan the QR code.